If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. What is the Great Attractor? Deep within the vastness of space, a phenomenon known as the Great Attractor beckons astronomers with its enigmatic gravitational pull. Imagine an unseen force, powerful enough to draw entire galaxies, including our own Milky Way, toward it, yet shrouded in mystery, hidden behind the dense dust and gas of the Milky Way's plane. What could possibly possess such immense gravitational power? At first glance, it's hard to grasp the sheer scale of this cosmic anomaly. The Great Attractor is not just some distant point in space. It is a region of concentrated gravitational force, situated roughly 150 to 250 million light-years away from Earth, in the direction of the constellation Norma. This isn't the kind of pull that affects just one star or one galaxy. Instead, it influences vast swaths of the cosmos, including entire superclusters of galaxies. And here's the kicker. Despite its profound effects, it remains largely invisible to us. The influence of an unseen giant. Galaxies across the observable universe are in constant motion, not just because of the cosmic expansion set in motion by the Big Bang, but also due to gravitational tugs from other massive objects. These motions aren't random. They're dictated by the gravitational interplay between visible matter, stars, planets, and gas, and the mysterious dark matter that permeates the universe. Observations reveal that the Milky Way, along with the surrounding local group of galaxies, is hurtling through space at nearly 600 kilometers per second. This astonishing speed is not just a result of the universe's expansion. It's also influenced by the pull of the Great Attractor. But here's the twist. The Great Attractor doesn't behave like a single object, such as a black hole or a single galaxy cluster. Instead, it appears to be a vast conglomeration of matter, possibly comprising multiple galaxy clusters and an enormous amount of dark matter. This complexity adds layers to the mystery. What are we being drawn toward? Is it a single dense region of matter? Or is it part of a larger structure, a cosmic domino effect leading to something even grander? The search for clues. The Great Attractor came to our attention not through direct observation, but through its influence. In the late 20th century, astronomers noticed something peculiar. The galaxies in our vicinity weren't moving in a way that aligned with theoretical expectations. Instead of flowing smoothly with the cosmic expansion, they exhibited a peculiar velocity, deviating from what the expansion alone would predict. It was as if some unseen hand was pulling them off course. This anomaly was one of the first clues to the existence of the Great Attractor. Even now, decades after its discovery, the Great Attractor is cloaked in secrecy, obscured by the Milky Way zone of avoidance, a region so thick with stars, dust, and gas that visible light telescopes struggle to see through it. To uncover the truth, scientists have turned to alternative methods like infrared and X-ray observations, which can penetrate the galactic veil. These tools have provided tantalizing glimpses of what lies beyond, but they have also raised more questions than answers. The pull of the unknown. So, what is the Great Attractor really? Could it be the core of a massive supercluster, an unfathomably dense concentration of galaxies? Or is it something more exotic, a region dominated by dark matter, or even phenomena we have yet to theorize? Its influence stretches across millions of light years, but the nature of this pull challenges our understanding of gravity and large-scale cosmic structures. Even as technology advances, the Great Attractor seems to recede further into mystery, offering only glimpses of its vast scale and gravitational dominance. For every new observation, there are countless new questions. Why does it exist where it does? What forces led to its formation? And what does its presence tell us about the universe as a whole? A deeper mystery awaits. As we gaze into the depths of space, the Great Attractor serves as a reminder of how much we have yet to learn. It challenges our scientific frameworks, forces us to develop new methods of observation, and compels us to confront the limits of our understanding. What we do know is tantalizing, but the true nature of this cosmic anomaly remains hidden, waiting for humanity's continued exploration to unlock its secrets. The discovery of a cosmic puzzle. In the tapestry of astronomical history, the discovery of the Great Attractor is a story marked by ingenuity, curiosity, and serendipity. It began as an enigma, a puzzle formed by peculiar motions of galaxies, motions that defied the expected patterns dictated by the cosmic expansion. But how did scientists even notice this anomaly in the vast, silent expanse of space? The first clues: peculiar velocities. In the mid-20th century, astronomers began to study the motion of galaxies with increasing precision. Edwin Hubble's earlier work had shown that the universe was expanding, a discovery that revolutionized our understanding of the cosmos. Galaxies, it seemed, were moving away from each other, their velocities proportional to their distances, as described by the Hubble-Emettra law. This expansion was thought to dominate the motion of all cosmic objects. Yet, as technology improved, discrepancies in this neat model began to emerge. Some galaxies weren't behaving as expected. They exhibited peculiar velocities, motions that couldn't be accounted for by cosmic expansion alone. These deviations hinted at additional gravitational forces acting on these galaxies, forces that were strong enough to tug them off course. The role of redshift and Doppler effects. The discovery of these peculiar velocities relied heavily on the study of redshifts. When galaxies move away from us, their light shifts toward the red end of the spectrum, a result of the Doppler effect. Conversely, galaxies moving toward us exhibit a blue shift. By measuring these shifts, astronomers can determine the speed and direction of a galaxy's motion relative to Earth. In the 1970s and 1980s, a group of astronomers studying the redshifts of galaxies noticed something intriguing. While most galaxies followed the expected expansion pattern, clusters of galaxies, including our own local group, seemed to be drawn toward a specific region of the sky. This region lay in the direction of the Hydra Centaurus supercluster. The gravitational pull emanating from this region suggested the presence of a massive concentration of matter, the first indirect evidence of what we now call the Great Attractor. Piecing together the puzzle. At this point, the mystery deepened. The peculiar velocities suggested an immense gravitational source, but where was it? The challenge of pinpointing the Great Attractor lay in its location. It sits behind the zone of avoidance, the part of the sky obscured by the dense plane of the Milky Way. This zone acts as a cosmic blind spot, hiding objects behind a curtain of stars, gas, and interstellar dust. To overcome this obstacle, astronomers began to use tools capable of peering through this veil. Infrared observations proved especially useful, as infrared light can penetrate the dust that blocks visible light. Later, X-ray telescopes added another layer of insight, revealing galaxy clusters and hot gas in regions previously unseen. These tools began to reveal the structure of the Hydra Centaurus supercluster and, with it, the gravitational influence of the Great Attractor. Discovering the Laniakea supercluster. One of the most significant breakthroughs came with the realization that the Great Attractor is part of an even larger structure. In 2014, astronomers mapping the flow of galaxies discovered the Laniakea supercluster, a massive network of galaxies spanning over 500 million light-years. The Milky Way, along with the local group and neighboring clusters, resides within this supercluster. The Great Attractor lies at its core, acting as the gravitational nexus that organizes the flow of galaxies within Laniakea. This discovery reshaped our understanding of cosmic structures. For decades, astronomers had studied galaxies and clusters as isolated systems. The revelation of superclusters and their dynamics demonstrated the interconnectedness of the universe on the largest scales. It also raised new questions. What lies beyond the Great Attractor? Are there even larger structures exerting influence on Laniakea itself? A growing mystery. Despite these advances, the Great Attractor remained elusive. Early surveys underestimated its complexity, often oversimplifying it as a single dense region of matter. Later observations suggested it might be a part of multiple overlapping structures, including the Shapley supercluster, a colossal concentration of galaxies further along the same cosmic flow. This raised another tantalizing possibility. Could the Great Attractor be part of an even larger cosmic hierarchy, a series of gravitational centers leading to something beyond? The limits of observation. The discovery of the Great Attractor also underscored the limitations of human observation. Even with advanced tools, much of the universe remains hidden from view. The zone of avoidance is just one example of how natural barriers, like interstellar dust, obscure our understanding. Dark matter and dark energy, which make up the majority of the universe, add another layer of mystery. These invisible forces influence the motion of galaxies and superclusters, but they remain largely theoretical, with little direct evidence to illuminate their role in phenomena like the Great Attractor. The allure of the unknown. The discovery of the Great Attractor represents a turning point in astronomy. It challenged existing models of galactic motion, introduced the concept of superclusters, and highlighted the interconnected nature of the universe. But it also left us with more questions than answers. What exactly is the Great Attractor? How did it form? And what does it mean for the ultimate fate of the cosmos? These questions continue to drive astronomers as they push the boundaries of observation and theory. Each new discovery brings us closer to understanding the Great Attractor. But like any great mystery, it also opens the door to new, uncharted territories. The deeper we look, the more we realize how much remains unknown, hidden in the shadows of the cosmos. The quest to understand the Great Attractor has always been a journey through uncharted territory. After its gravitational pull was detected through peculiar velocities, astronomers were left with a daunting task: to decipher the nature of an object so massive, yet obscured from direct observation. This enigma forced scientists to innovate, creating new ways to see through the dense plane of the Milky Way and unlock the secrets hidden behind the zone of avoidance. Infrared astronomy became one of the most powerful tools in this pursuit. Unlike visible light, infrared wavelengths can pass through interstellar dust, revealing objects otherwise hidden. Early surveys using infrared telescopes provided the first detailed glimpses of the region where the Great Attractor resides. These observations showed clusters of galaxies, their light faint and redshifted due to their immense distances. But even with this progress, the Great Attractor itself remained elusive, as if its true nature was cloaked by layers of cosmic complexity. X-ray astronomy added another dimension to the search. Observing in the X-ray spectrum allows scientists to detect high-energy phenomena, such as the hot gas that permeates galaxy clusters. This gas, heated to millions of degrees, emits X-rays that can be detected even through the dense galactic plane. Surveys conducted with X-ray observatories, such as Rosat and later Chandra, revealed more about the massive structures in the vicinity of the Great Attractor. These structures, brimming with thousands of galaxies, seem to converge toward a common gravitational center, reinforcing the idea that something extraordinary lay at the heart of this region. One of the most intriguing discoveries was the realization that the Great Attractor is not an isolated feature. Instead, it appears to be part of a much larger network of structures, interconnected by gravity. The Laniakea supercluster, identified in 2014, redefined our understanding of the cosmic web. Spanning over 500 million light-years, Laniakea includes the Milky Way, the Local Group, and numerous neighboring clusters, all moving along a gravitational flow toward the Great Attractor. This discovery placed the Great Attractor within a larger context, suggesting that its influence is part of a grander cosmic design. The discovery of Laniakea raised profound questions about the structure of the universe. For decades, astronomers had assumed that galaxy clusters were relatively isolated, with their motions governed solely by local gravitational forces. The identification of superclusters and their flows toward massive attractors revealed a level of organization that few had anticipated. The Great Attractor, rather than being an anomaly, appeared to be a critical node in this vast network. Even as the scope of the mystery expanded, the fundamental questions about the Great Attractor remained unanswered. What exactly is it? Is it a dense core of galaxies, or does its mass consist primarily of dark matter? Observations suggest that visible matter, such as stars and gas, cannot account for the Great Attractor's immense gravitational pull. This discrepancy points to the presence of dark matter, an invisible substance that makes up about 27% of the universe's total mass and energy. Dark matter's role in the Great Attractor is one of the most compelling aspects of this puzzle, but its nature remains largely speculative. Another compelling clue emerged with the identification of the Shapley supercluster. Located beyond the Great Attractor, the Shapley supercluster is one of the most massive known structures in the observable universe. Its gravitational influence is so immense that some scientists believe it may overshadow the Great Attractor itself. This raises the tantalizing possibility that the Great Attractor is not the ultimate destination of the cosmic flow, but rather a waypoint on a journey toward an even greater gravitational center. The interplay between the Great Attractor and the Shapley supercluster adds a layer of complexity to our understanding of cosmic dynamics. It suggests that the universe is not only a web of interconnected structures, but also a cascade of gravitational interactions, with smaller attractors feeding into larger ones. This hierarchical structure challenges traditional models and forces astronomers to reconsider how galaxies and superclusters evolve over billions of years. The Great Attractor also presents a philosophical challenge. It serves as a reminder of the limitations of human perception and the vastness of the universe. Despite all our technological advancements, we are still groping in the dark, piecing together fragments of information to form an incomplete picture. The Great Attractor, hidden behind the zone of avoidance, symbolizes the boundaries of our knowledge and the mysteries that lie beyond. As scientists continue their search, they are not just uncovering facts about the Great Attractor, they are also redefining our place in the universe. The motions of galaxies, the flows of superclusters, and the gravitational forces that shape the cosmos all point to a reality that is far more interconnected and dynamic than we ever imagined. Each new discovery is a step closer to understanding the Great Attractor, but it also reveals how much more there is to learn. The pull of the Great Attractor is not limited to the Milky Way or even our local group of galaxies. Its gravitational influence extends across vast distances, impacting galaxies and clusters hundreds of millions of light-years away. Understanding this reach has required astronomers to study the peculiar velocities of galaxies, motions that deviate from the expected flow of cosmic expansion. These deviations have provided a map of sorts, tracing the paths of galaxies as they move toward this enigmatic gravitational center. One of the most striking revelations about the Great Attractor is the sheer scale of its impact. The Milky Way and its neighboring galaxies, part of the local group, are being drawn toward the Hydra-Centaurus supercluster, which itself is part of a much larger flow directed toward the Great Attractor. This movement, combined with the gravitational pull of other massive structures like the Shapley supercluster, creates a complex interplay of forces that defines the motion of galaxies across vast cosmic distances. The peculiar velocity of our galaxy, moving at around 600 kilometers per second, is just one piece of this puzzle. By studying the motion of other galaxies in the same direction, astronomers have been able to infer the presence of a massive concentration of matter at the heart of the Great Attractor. However, the exact nature of this matter remains a mystery. Observations suggest that visible galaxies and gas cannot account for the total gravitational force, pointing to a significant contribution from dark matter. Dark matter, the elusive substance that interacts with regular matter only through gravity, plays a central role in the dynamics of the Great Attractor. While it cannot be seen or directly detected, its presence is inferred from its effects on the motion of galaxies. The distribution of dark matter in and around the Great Attractor likely forms a dense, invisible web that binds galaxies together and drives their motion toward this gravitational center. As astronomers have mapped these motions, they have also discovered patterns that suggest the Great Attractor is part of a much larger structure. The Laniakea supercluster, of which the Great Attractor is a key component, organizes the flow of galaxies over hundreds of millions of light-years. This vast structure is not static. It evolves over time, with galaxies converging toward denser regions under the influence of gravity. The Great Attractor represents one such dense region, but it is likely part of a hierarchical network of attractors and superclusters. The study of the Great Attractor has also led to surprising discoveries about the interplay between gravity and other cosmic forces. While gravity pulls galaxies together, the expansion of the universe, driven by dark energy, pushes them apart. This cosmic tug-of-war shapes the large-scale structure of the universe, creating a dynamic balance between attraction and repulsion. The Great Attractor's role in this balance is particularly intriguing, as its gravitational pull must contend with the accelerating expansion of the universe. The Shapley supercluster, located beyond the Great Attractor, complicates this picture further. Its immense gravitational influence suggests that it may be the true endpoint of the cosmic flow, with the Great Attractor acting as an intermediary. This raises fascinating questions about the scale and structure of the universe. Are there even larger attractors beyond Shapley? How do these structures interact over cosmic timescales? And what does this tell us about the evolution of the universe? Astronomers have also explored the possibility that the Great Attractor is not a single, cohesive entity, but a composite of multiple overlapping structures. This would explain the complexity of its gravitational influence, which appears to vary across different regions. Such a scenario aligns with the idea of the cosmic web, where galaxies and clusters are connected by filaments of matter, and dense nodes like the Great Attractor represent intersections in this vast network. Technological advances continue to push the boundaries of what we can observe and understand about the Great Attractor. Next-generation telescopes, capable of observing in multiple wavelengths, promise to provide clearer views of this hidden region. Instruments like the James Webb Space Telescope and upcoming radio observatories will help astronomers probe deeper into the zone of avoidance, uncovering new details about the galaxies and matter within. Yet, despite these advancements, the Great Attractor remains a profound mystery. Its gravitational pull is undeniable, but its true nature eludes us. Is it primarily a collection of galaxies, or does dark matter dominate its mass? Could it be part of an even larger structure that extends beyond our current observational limits? These questions drive ongoing research, pushing scientists to develop new theories and methods. The study of the Great Attractor is not just a quest for answers. It is a journey that redefines our understanding of the universe. Each discovery reveals the interconnectedness of cosmic structures, showing how galaxies, clusters, and superclusters are bound together by invisible forces. The Great Attractor, with its immense gravitational power, stands as a testament to the complexity and beauty of the cosmos. The more astronomers delve into the mystery of the Great Attractor, the more they encounter the interplay of hidden forces shaping the universe. Chief among these forces is dark matter, an enigmatic substance that does not emit or absorb light, making it invisible to conventional observation. Despite its elusiveness, dark matter's gravitational effects are evident on cosmic scales, influencing the motion of galaxies, the formation of clusters, and the structure of the universe itself. Its role in the Great Attractor is critical, yet its precise nature remains one of the greatest unsolved mysteries in astrophysics. When astronomers attempt to calculate the mass of the Great Attractor using only visible matter, galaxies, stars, and intergalactic gas, they find a glaring discrepancy. The gravitational pull exerted by the Great Attractor far exceeds what visible matter alone can account for. This discrepancy suggests that dark matter must make up a significant portion of the mass in this region. However, the exact distribution and density of dark matter around the Great Attractor remains speculative, adding another layer of complexity to the mystery. The concept of dark matter itself is as revolutionary as it is perplexing. It does not interact with electromagnetic forces, meaning it cannot be seen or felt directly. Instead, its existence is inferred through its gravitational effects. Galaxy rotation curves, gravitational lensing, and peculiar velocities all point to the presence of dark matter, shaping the dynamics of the universe on scales ranging from individual galaxies to superclusters like Laniakea. In the case of the Great Attractor, dark matter likely forms a dense halo that contributes significantly to its gravitational influence. Adding to the complexity is the idea that dark matter may not be evenly distributed, but instead concentrated in clumps or filaments that align with the cosmic web. This structure, composed of interconnected filaments of matter, spans the universe, with nodes where these filaments intersect forming dense regions like the Great Attractor. If the Great Attractor is indeed a node in this web, its gravitational pull could be amplified by the cumulative effects of dark matter along these filaments. But dark matter is only one piece of the puzzle. The discovery of dark energy, a mysterious force driving the accelerated expansion of the universe, introduces another layer of intrigue. Dark energy works in opposition to gravity, pushing galaxies apart rather than drawing them together. Its influence becomes dominant on the largest cosmic scales, but the Great Attractor represents a region where gravity temporarily overpowers this expansive force, creating a local convergence of galaxies. This interplay between dark matter and dark energy raises profound questions about the ultimate fate of structures like the Great Attractor. Will its gravitational pull continue to draw galaxies inward, forming an ever-denser region of space? Or will the accelerating expansion of the universe eventually overcome this pull, halting the motion of galaxies and dispersing them into the cosmic void? These scenarios hinge on the precise nature and balance of dark matter and dark energy, both of which remain poorly understood. Complicating matters further is the possibility that the Great Attractor is not a singular object, but a composite of multiple overlapping structures. The Shapley supercluster, located beyond the Great Attractor, may exert a competing gravitational influence, pulling galaxies away from the Great Attractor's center. This creates a complex flow of matter, with galaxies moving along trajectories shaped by the combined effects of multiple gravitational sources. Understanding these flows requires sophisticated models that account for the interactions of visible matter, and dark energy. Despite these challenges, astronomers are making progress. Advanced simulations of the universe's evolution, combined with high-resolution observations, are shedding light on the behavior of matter around the Great Attractor. By studying the motion of galaxies and clusters in greater detail, scientists are beginning to map the gravitational landscape of this region, revealing the intricate dance of forces at play. Perhaps one of the most intriguing aspects of the Great Attractor is its role in the broader cosmic hierarchy. While it exerts a powerful gravitational pull on nearby galaxies, it may itself be moving toward an even larger attractor, such as the Shapley supercluster or another, yet undiscovered structure. This cascading flow of matter highlights the interconnectedness of the universe, with smaller structures feeding into larger ones in a process that spans billions of years. The Great Attractor also challenges our philosophical understanding of the cosmos. It reminds us that the universe is not a static or uniform place, but a dynamic and evolving system. The forces that shape it operate on scales that are almost incomprehensible, both in terms of time and space. Yet, within this vastness, there is a profound order, a web of connections that ties galaxies, clusters, and superclusters together. As we continue to explore the Great Attractor, we are not just uncovering facts about a distant region of space. We are also expanding the boundaries of human knowledge, probing the very nature of matter, energy, and gravity. The Great Attractor is more than a scientific puzzle. It is a window into the forces that govern the universe, a reminder of the mysteries that lie beyond our current understanding. The Great Attractor, despite its gravitational influence on galaxies over hundreds of millions of light years, remains shrouded in mystery, largely because of its location. Situated behind the dense plain of the Milky Way, it is obscured by what astronomers call the zone of avoidance. This region, thick with interstellar dust, gas, and countless stars, blocks visible light from reaching our telescopes. For decades, this cosmic blind spot has posed one of the greatest challenges in unraveling the true nature of the Great Attractor. To penetrate this veil, astronomers have turned to wavelengths of light that can bypass these obstacles. Infrared and X-ray observations have proven particularly effective. Infrared light, with its longer wavelengths, can pass through the interstellar dust that absorbs visible light. Infrared surveys conducted by telescopes, such as the Wide Field Infrared Survey Explorer, WISE, have provided detailed maps of the hidden galaxies in the zone of avoidance. These observations have revealed clusters of galaxies previously undetected, offering tantalizing hints about the Great Attractor's structure. X-ray astronomy takes a different approach. While infrared light helps reveal stars and galaxies, X-rays are emitted by extremely hot gas, such as the kind found in galaxy clusters. This gas, heated to millions of degrees by gravitational interactions, emits high-energy radiation that can penetrate the zone of avoidance. Observatories like Chandra and Newton have detected this X-ray glow, providing another layer of evidence for the massive concentrations of matter in the Great Attractor's region. But even with these advanced tools, the Great Attractor remains elusive. Observations suggest that it is not a single, compact object like a black hole or a single galaxy cluster. Instead, it appears to be a sprawling region of space, encompassing multiple galaxy clusters, intergalactic gas, and, most intriguingly, a vast amount of dark matter. This complex composition makes it difficult to determine its exact boundaries and mass, adding to the enigma. One of the most striking features revealed by these observations is the motion of galaxies in the region. Galaxies around the Great Attractor are not simply orbiting a central point. They're being drawn along intricate paths, shaped by the gravitational interplay of visible matter, dark matter, and the expanding universe. These paths form a part of what scientists call the cosmic flow, a large-scale movement of matter that defines the dynamics of superclusters and their components. The Ionia Chaos supercluster, of which the Great Attractor is a core feature, is a prime example of this flow. Galaxies within Ionia move along gravitational pathways that converge toward the Great Attractor, much like rivers flowing toward a central basin. However, this flow is not uniform. Some regions show evidence of counterflows or competing gravitational influences, particularly from structures like the Shapley supercluster, located farther along the same cosmic axis. These competing forces create a dynamic, ever-shifting gravitational landscape. The role of dark matter in this process cannot be overstated. While visible galaxies and gas contribute to the gravitational pull, they represent only a fraction of the total mass. The rest is thought to be made up of dark matter, an invisible substance that forms the scaffolding of the universe. Dark matter's distribution around the Great Attractor is inferred from the motion of galaxies and the gravitational lensing effects it produces, bending light from distant objects as it passes through these dense regions. Another critical factor is the presence of intergalactic gas. This gas, while less massive than dark matter, contributes to the gravitational pull and provides key observational evidence through its X-ray emissions. Studying this gas has revealed temperature and density variations that correspond to the gravitational interactions between galaxy clusters. These variations offer clues about the past collisions and mergers that have shaped the Great Attractor over billions of years. As astronomers refine their models, one possibility emerges with increasing clarity. The Great Attractor may not be a destination in itself, but part of a larger, interconnected system. Its gravitational pull may be linked to even larger structures beyond, such as the Shapley supercluster. This cascading hierarchy of attractors suggests that the universe is organized into layers of gravitational influence, with smaller structures feeding into larger ones in a process that continues across vast distances and timescales. This interconnectedness highlights the complexity of the cosmic web, a vast network of filaments, voids, and nodes that defines the large-scale structure of the universe. The Great Attractor, located at one of these nodes, represents a focal point where matter converges, but it is not isolated. Filaments of dark matter and galaxies stretch out from it, connecting it to other nodes like Shapley and beyond. Understanding these connections is crucial for piecing together the broader picture of the universe's evolution. Despite these advances, many questions remain unanswered. What exactly lies at the heart of the Great Attractor? Is it primarily composed of dark matter, or is there an unseen concentration of visible matter yet to be discovered? How did such a massive structure form? And what does its presence tell us about the early universe? These questions drive ongoing research, pushing the limits of observational astronomy and theoretical physics. The mystery of the Great Attractor is not just a scientific challenge. It is a profound reminder of how much we have yet to learn about the universe. As our tools and techniques improve, we come closer to uncovering its secrets, but the journey is far from over. Each new discovery opens up new questions, revealing the intricate dance of forces that shape the cosmos and reminding us of the vast unknown that lies beyond. The Great Attractor is not merely a gravitational anomaly. It is a window into the complexities of cosmic motion. Galaxies, clusters, and superclusters are not static entities. They are constantly in motion, influenced by gravitational forces that stretch across millions of light years. The peculiar velocities of galaxies, their deviations from the predicted motions based solely on the universe's expansion, have become key to understanding the Great Attractor and the larger structures of the cosmos. When astronomers first began to study the motion of galaxies in detail, they noticed a peculiar pattern. Instead of simply following the expansion of the universe, certain galaxies appeared to move toward a specific region of space. This motion was subtle yet unmistakable, providing an early hint of the gravitational pull exerted by the Great Attractor. To measure these motions, astronomers used redshifts, which indicate how fast an object is moving away from us. By comparing redshift data to the expected values based on the universe's expansion, they could identify deviations and infer the presence of unseen gravitational influences. One of the most significant findings came from the study of the Local Group, the cluster of galaxies that includes the Milky Way. The Local Group is moving at an astonishing speed of about 600 kilometers per second toward the Great Attractor. This motion is part of a larger flow that encompasses the Virgo cluster and other nearby groups, forming a complex dance of galaxies drawn together by the gravitational forces of the Great Attractor. The concept of peculiar velocity has been crucial in mapping the large-scale structure of the universe. By studying the peculiar velocities of galaxies in different regions, astronomers can trace the gravitational influence of massive structures like the Great Attractor. This method has revealed not only the pull of the Great Attractor, but also the presence of other, even larger attractors, such as the Shapley supercluster. These findings suggest that the Great Attractor is part of a hierarchy of gravitational centers, each influencing the motion of galaxies over vast distances. The motion of galaxies is not simply a straight path toward the Great Attractor. Instead, it follows intricate patterns shaped by the interplay of gravitational forces. These patterns reveal the presence of filaments of matter connecting galaxies and clusters, forming the cosmic web. The Great Attractor lies at a node in this web, where multiple filaments converge. Galaxies within these filaments are drawn along these pathways, creating a flow that ultimately leads toward the Great Attractor. However, the motion of galaxies toward the Great Attractor is not unopposed. Dark energy, the mysterious force driving the accelerated expansion of the universe, works against gravity, pushing galaxies apart. On the largest scales, dark energy dominates, causing the universe to expand at an ever-increasing rate. But within regions like the Great Attractor, gravity temporarily overcomes this expansive force, pulling galaxies together. This delicate balance between gravity and dark energy shapes the dynamics of the universe and determines the fate of structures like the Great Attractor. The study of cosmic flows has also revealed the interconnectedness of the universe. Galaxies are not isolated entities. They are part of a vast network of matter that spans the cosmos. The Great Attractor, as a gravitational nexus, exemplifies this interconnectedness. Its influence extends across millions of light years, drawing galaxies from multiple directions. Yet, it is also connected to larger structures beyond, such as the Shapley supercluster, creating a cascade of gravitational interactions that defines the motion of galaxies on a cosmic scale. Advanced simulations have helped astronomers visualize these flows and understand the forces at play. These simulations use data from galaxy surveys, redshift measurements, and models of dark matter to recreate the motion of galaxies in 3 dimensions. They show how matter converges toward regions of high density, forming structures like the Great Attractor, while also highlighting the effects of competing forces, such as the pull of other attractors and the push of dark energy. Despite these advances, the true nature of the Great Attractor remains elusive. Observations suggest that it is not a singular object, but a region of concentrated mass, composed of galaxy clusters, dark matter, and intergalactic gas. Its gravitational pull is a cumulative effect of these components, but their exact distribution and composition are still uncertain. Dark matter, in particular, plays a critical role, forming the invisible scaffolding that binds galaxies together. Understanding the distribution of dark matter around the Great Attractor is key to unraveling its mystery. The Great Attractor also raises questions about the long-term evolution of the universe. Will its gravitational pull continue to draw galaxies inward, forming an even denser structure? Or will the accelerating expansion of the universe eventually overcome this pull, dispersing galaxies into the cosmic void? These questions touch on the fundamental nature of gravity, dark energy, and the fate of the cosmos itself. The study of the Great Attractor is not just a scientific endeavor. It is a testament to humanity's curiosity and drive to understand the universe. Each discovery about its nature and influence brings us closer to a deeper understanding of the cosmos. Yet, it also reminds us of the vastness and complexity of the universe, where mysteries like the Great Attractor challenge our knowledge and inspire us to keep exploring. The more we unravel the mystery of the Great Attractor, the more apparent it becomes that this massive region of gravitational pull is not an isolated phenomenon. It is part of a vast, interconnected cosmic web that ties galaxies, clusters, and superclusters together in a delicate balance of forces. This interconnectedness offers a glimpse into the structure and dynamics of the universe on its grandest scales, revealing a tapestry woven from the interplay of gravity, dark matter, and the expansion of space itself. One of the most fascinating aspects of the Great Attractor is its relationship to the cosmic web. The universe, on its largest scales, is not a random scattering of galaxies, but a highly organized network of filaments, voids, and nodes. These filaments, composed of dark matter and galaxies, stretch across hundreds of millions of light years, connecting dense regions of matter like superclusters. The Great Attractor occupies one of these nodes, where multiple filaments converge, creating a gravitational focal point that draws matter from vast distances. This structure challenges our understanding of how the universe evolved. The cosmic web is thought to have formed from tiny density fluctuations in the early universe, amplified by the effects of gravity over billions of years. Regions of slightly higher density attracted more matter, growing into the vast filaments and nodes we observe today. The Great Attractor, as a dense node in this web, is a product of this process, a testament to the power of gravity to shape the cosmos over unimaginable timescales. However, the Great Attractor's role within this web is not purely passive. Its immense gravitational pull influences the motion of galaxies and clusters within its reach, redirecting their paths and shaping the flows of matter across the universe. These flows are not random, but follow the contours of the cosmic web, with galaxies moving along filaments toward nodes like the Great Attractor. This movement creates a dynamic, ever-evolving structure, where matter continuously converges on dense regions while voids between filaments grow larger. The discovery of the Great Attractor's connection to larger structures, such as the Shapley supercluster, highlights the hierarchical nature of the universe. While the Great Attractor is a major gravitational center, it is not the end of the story. Beyond it lies the Shapley supercluster, one of the most massive structures in the observable universe. The gravitational influence of Shapley extends even farther, suggesting that the Great Attractor may itself be part of a larger flow, drawn toward this even denser region of space. This cascading hierarchy raises profound questions about the ultimate scale of the universe's structure. Are there attractors beyond Shapley, forming an even larger network of gravitational centers? If so, how far does this hierarchy extend, and what governs its organization? These questions push the boundaries of our understanding, challenging us to look deeper into the cosmos and refine our models of its evolution. Dark matter plays a crucial role in this hierarchy. As the invisible backbone of the cosmic web, dark matter provides the gravitational framework that shapes the motion of galaxies and clusters. Its distribution around the Great Attractor and along the filaments connecting it to other structures determines the flows of matter within this region. Yet, despite its importance, dark matter remains one of the greatest mysteries in physics. We know it exists and influences the universe on vast scales, but its true nature eludes us, leaving scientists to speculate about its composition and origins. Another factor shaping the Great Attractor's role in the cosmic web is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy acts in opposition to gravity, pushing galaxies apart and creating a tension between attraction and expansion. This interplay determines the fate of structures like the Great Attractor. While gravity continues to draw matter inward, dark energy works against it, gradually weakening its pull over time. The balance between these forces will ultimately decide whether the Great Attractor grows into an even larger structure or fades as galaxies drift apart. Observational advancements have been instrumental in revealing the Great Attractor's place within the cosmic web. High-resolution surveys, using instruments capable of detecting infrared, X-rays, and radio waves, have mapped the motion of galaxies and the distribution of matter across vast regions of space. These observations have provided detailed insights into the structure of the Great Attractor and its connections to neighboring nodes and filaments. They have also uncovered the presence of hot gas in and around the Great Attractor, further evidence of its gravitational influence in past interactions, such as collisions and mergers with other clusters. These collisions and mergers have likely played a significant role in shaping the Great Attractor. Galaxy clusters within its region are not static entities. They interact, collide, and merge over billions of years, creating shockwaves that heat intergalactic gas to extreme temperatures. These events leave behind observable signatures, such as X-ray emissions and distortions in the distribution of matter, offering clues about the history and dynamics of the Great Attractor. Despite these advancements, many mysteries remain. What exactly lies at the heart of the Great Attractor? Is it dominated by dark matter? Or does it contain a hidden concentration of visible matter, such as undiscovered galaxies or massive black holes? How does its mass compare to that of larger structures like the Shapley supercluster? And what does this tell us about the distribution of matter in the universe? The answers to these questions will not only illuminate the nature of the Great Attractor, but also provide deeper insights into the fundamental forces that shape the cosmos. Each discovery brings us closer to understanding the universe's intricate design, revealing the interconnectedness of its structures and the forces that drive its evolution. The Great Attractor represents not just a gravitational anomaly, but a cornerstone in the larger understanding of the universe's organization. As astronomers have continued their exploration, they've begun to uncover patterns that suggest the Great Attractor is not an isolated feature, but a part of a vast, interconnected network of superclusters and cosmic flows. These revelations bring new questions about its ultimate purpose and place in the ever-evolving tapestry of the cosmos. The discovery of the Laniakea supercluster was a turning point in this understanding. Encompassing over 100,000 galaxies, including the Milky Way, Laniakea is a gravitationally bound region stretching more than 500 million light-years. Within this supercluster, galaxies are not scattered randomly. Instead, they follow coherent flows, drawn along gravitational pathways that converge toward the Great Attractor. This discovery redefined how we see our own location in the universe, placing us within a larger context of cosmic motion. The boundaries of Laniakea are not rigid. They are defined by the gravitational influences that govern the motion of galaxies. These influences create distinct regions of attraction, where galaxies are drawn toward a central point. The Great Attractor is one such point, but it is not the only one. The Shapley supercluster, located farther along the same axis, represents an even more massive concentration of matter, challenging the dominance of the Great Attractor and shaping the flow of galaxies within Laniakea. This realization has profound implications for our understanding of the universe's large-scale structure. It suggests that the Great Attractor is part of a hierarchical network, where smaller attractors feed into larger ones. This hierarchy is mirrored in the distribution of matter, from individual galaxies to clusters, superclusters, and beyond. Each level of this hierarchy contributes to the overall motion of the cosmos, creating a dynamic interplay of forces that evolves over billions of years. The role of dark matter in this hierarchy is crucial. As the unseen scaffolding of the universe, dark matter provides the gravitational framework that binds galaxies together and shapes their motion. Within Laniakea, the distribution of dark matter forms the filaments and nodes of the cosmic web, directing the flow of galaxies toward dense regions like the Great Attractor. Understanding the distribution of dark matter around the Great Attractor is a key challenge for astronomers, requiring advanced simulations and observations to reveal its influence. Dark energy, the mysterious force driving the accelerated expansion of the universe, adds another layer of complexity. While gravity pulls galaxies together, dark energy pushes them apart, creating a delicate balance between attraction and repulsion. On the scales of superclusters like Laniakea, gravity dominates, allowing structures like the Great Attractor to form and grow. However, on larger scales, dark energy's influence becomes stronger, raising questions about the long-term fate of the Great Attractor and other massive structures. The interplay between gravity and dark energy has profound implications for the future of the universe. If dark energy continues to accelerate the expansion of the universe, it could eventually overpower the gravitational pull of structures like the Great Attractor, halting the flow of galaxies and isolating them in an ever-expanding void. Alternatively, if dark energy weakens or changes over time, gravitational forces could dominate, leading to a future where galaxies continue to converge toward massive attractors like the Great Attractor. To understand these dynamics, astronomers have turned to advanced tools and methods. Observations from telescopes capable of detecting infrared, X-rays, and radio waves have provided detailed maps of the Great Attractor and its surrounding regions. These maps reveal not only the distribution of visible matter, but also the motion of galaxies and the presence of intergalactic gas, heated to extreme temperatures by gravitational interactions. By combining these observations with simulations, scientists are piecing together a comprehensive picture of the Great Attractor's role in the cosmic web. One of the most intriguing aspects of this research is the discovery of additional structures connected to the Great Attractor. Beyond the Shapley supercluster, astronomers have identified other massive regions of matter, suggesting that the Great Attractor is part of an even larger system. These discoveries hint at the existence of a superhierarchy of attractors, where each structure is linked to others through the flow of matter across the cosmic web. This interconnectedness raises profound philosophical questions about the nature of the universe. What is the ultimate scale of this hierarchy? Are there limits to the structures we can observe, or does the cosmic web extend indefinitely? These questions challenge our understanding of the cosmos and push the boundaries of our scientific imagination. As we continue to study the Great Attractor, we are not only uncovering the secrets of a distant region of space, but also gaining insights into the forces that shape the universe as a whole. Each discovery brings us closer to answering fundamental questions about the nature of gravity, dark matter, and dark energy. At the same time, it reveals the incredible complexity and beauty of the cosmos, reminding us of the vast unknown that still lies beyond our reach. The Great Attractor is not only a gravitational centerpiece for our local cosmic neighborhood, but also a key player in the story of galactic evolution. Understanding its effects extends beyond mapping motion or pinpointing mass. It reveals how galaxies, clusters, and superclusters interact, collide, and transform over billions of years. The forces at work within the Great Attractor's reach are not just theoretical. They are tangible drivers of cosmic change, shaping the very fabric of the universe. One of the most significant processes linked to the Great Attractor is the formation and evolution of galaxy clusters. These clusters, comprising hundreds or even thousands of galaxies, are held together by the immense gravitational pull of dark matter. Within the Great Attractor's sphere of influence, clusters form dense regions of matter, often colliding and merging over time. These collisions are among the most energetic events in the universe, releasing enormous amounts of heat and creating shockwaves that ripple through intergalactic space. When galaxy clusters collide, their interactions create observable phenomena that provide critical clues about the underlying forces at play. For example, the hot gas within clusters, heated to millions of degrees during collisions, emits X-rays detectable by space-based telescopes. This gas often shows evidence of turbulence and compression, indicating the scale and intensity of the interactions. By studying these emissions, astronomers can map the distribution of matter within clusters and understand the dynamics of their mergers. These collisions also reveal the behavior of dark matter, which plays a dominant role in the evolution of galaxy clusters. Unlike visible matter, dark matter does not interact through electromagnetic forces, meaning it passes through collisions largely unaffected. This behavior creates a unique signature that astronomers can detect through gravitational lensing, the bending of light from distant objects as it passes through a region of dark matter. Observing these lensing effects in and around the Great Attractor provides valuable insights into the distribution and properties of dark matter within this region. The motion of galaxies toward the Great Attractor also affects their internal structures and star formation rates. As galaxies move through the dense intergalactic medium, they experience a phenomenon known as ram pressure stripping. This process occurs when a galaxy's movement through hot gas exerts a force that strips away its outer layers of gas, effectively quenching its ability to form new stars. Over time, this can transform star-forming spiral galaxies into more passive elliptical galaxies, altering the population of galaxies within the Great Attractor. At the same time, the gravitational interactions between galaxies can trigger bursts of star formation. When galaxies pass close to one another or collide, their mutual gravitational pull can distort their shapes, compressing gas and igniting waves of new star formation. These interactions, though chaotic, often lead to the creation of brilliant starburst galaxies and can fuel the growth of supermassive black holes at the centers of galaxies. The presence of such supermassive black holes adds another layer of complexity to the Great Attractor's dynamics. These black holes, millions or even billions of times the mass of the Sun, play a significant role in regulating star formation and shaping their host galaxies. As matter falls into a supermassive black hole, it releases immense energy in the form of jets and radiation, which can heat the surrounding gas and prevent it from cooling and forming new stars. This feedback mechanism creates a delicate balance between star formation and quenching, influencing the long-term evolution of galaxies within the Great Attractor. The interplay between gravity, dark matter, and gas dynamics in the Great Attractor region is also crucial for understanding its overall structure. Observations suggest that the Great Attractor is not a single, cohesive object, but a composite of multiple overlapping clusters and filaments. These components interact through gravitational forces, creating a complex web of connections that defines the motion of galaxies and the distribution of matter. Adding to this complexity is the influence of the Shapley supercluster, located beyond the Great Attractor. The Shapley supercluster's immense gravitational pull may compete with that of the Great Attractor, creating a dynamic tug-of-war that shapes the motion of galaxies within their overlapping spheres of influence. Understanding this interplay requires detailed observations and sophisticated simulations, which can recreate the motion of galaxies and the distribution of matter in 3 dimensions. As technology advances, astronomers are developing new tools to study the Great Attractor in greater detail. Instruments capable of detecting faint X-rays, infrared light, and radio waves are providing a clearer view of the structures hidden within the zone of avoidance. These observations are complemented by large-scale galaxy surveys, which map the motion and distribution of galaxies across vast regions of space. Together, these tools are helping to unravel the mysteries of the Great Attractor and its role in the cosmic web. Yet, despite these advances, many fundamental questions remain unanswered. What lies at the core of the Great Attractor? Is it dominated by visible galaxies, or does dark matter form the majority of its mass? How does its mass compare to other structures in the universe, such as the Shapley supercluster? And what does its existence tell us about the formation and evolution of the universe on its largest scales? The Great Attractor continues to challenge our understanding of the cosmos, serving as a focal point for some of the most profound questions in astronomy. Each discovery about its nature and influence not only deepens our knowledge of the universe, but also highlights the intricate interplay of forces that govern its evolution. The journey to understand the Great Attractor is far from over, but every step brings us closer to uncovering the secrets of this mysterious region and the larger story of the cosmos. As the Great Attractor draws galaxies toward it, it unveils not only its gravitational influence, but also its profound implications for our understanding of the universe's architecture. This enigmatic region offers a rare glimpse into the forces shaping cosmic evolution, linking the observable universe to theoretical models that attempt to explain its vast complexity. The pursuit of understanding the Great Attractor has led astronomers to explore not only its immediate surroundings, but also the larger structures to which it belongs, raising fundamental questions about the interconnectedness of the cosmos. One of the most compelling aspects of studying the Great Attractor is its relationship with the cosmic web, the large-scale structure of the universe. The web is a network of filaments composed of galaxies and dark matter, interspersed with vast voids of nearly empty space. These filaments converge at dense nodes, forming superclusters like Laniakea and Shapley. The Great Attractor resides at one of these nodes, anchoring the flow of matter within its region while simultaneously being influenced by the gravitational pull of adjacent structures. This interconnectedness suggests that the Great Attractor is not an isolated phenomenon, but part of a larger, hierarchical network of attractors. The Shapley supercluster, located beyond the Great Attractor, represents an even larger node in this network, exerting its own gravitational influence over galaxies and clusters within its reach. The motion of galaxies within the Great Attractor's domain may be influenced by this larger structure, creating a dynamic interplay of forces that shapes the cosmic flow. The discovery of this hierarchy challenges traditional models of the universe's organization. For much of modern astronomy's history, galaxies were thought to be relatively independent, their motion governed primarily by local interactions. The revelation of superclusters and the cosmic web introduced a new paradigm, emphasizing the role of large-scale structures and their gravitational interplay. The Great Attractor and its relationship to the Shapley supercluster exemplify this paradigm, offering a case study in how gravity organizes matter on the grandest scales. Adding to this complexity is the role of dark matter, which forms the invisible scaffolding of the cosmic web. While visible galaxies provide a roadmap of the web's structure, dark matter accounts for the majority of its mass and dictates the flow of matter within it. Observations suggest that the Great Attractor's gravitational pull is amplified by a dense concentration of dark matter, which shapes the paths of galaxies and clusters converging toward it. Understanding this distribution of dark matter is critical to unraveling the Great Attractor's nature and its place in the cosmic hierarchy. Dark energy, the force driving the universe's accelerated expansion, further complicates this picture. On the largest scales, dark energy dominates, causing galaxies and clusters to move apart. However, within regions like the Great Attractor, gravity temporarily overcomes this expansive force, allowing matter to converge and form dense structures. This balance between attraction and expansion highlights the delicate interplay of forces that governs the universe's evolution. The Great Attractor serves as a microcosm of this balance, illustrating how gravity can still dominate on local scales despite the overarching influence of dark energy. The study of the Great Attractor has also provided new insights into the history and evolution of the universe. By mapping the motion of galaxies and clusters within its region, astronomers have reconstructed the past interactions that shaped this gravitational anomaly. Collisions and mergers between galaxy clusters have left observable signatures, such as shockwaves in the hot gas that permeates intergalactic space. These signatures offer a glimpse into the violent processes that built the Great Attractor over billions of years, shedding light on the dynamics of large-scale structure formation. At the same time, these observations raise questions about the future of the Great Attractor. Will its gravitational pull continue to draw matter inward, growing into an even larger structure? Or will the accelerating expansion of the universe eventually overcome this pull, halting the flow of galaxies and isolating them in an ever-expanding void? The answers to these questions depend on the relative strengths of gravity, dark matter, and dark energy, as well as the interactions between these forces on different scales. One of the most intriguing possibilities is that the Great Attractor itself is part of a larger, interconnected system of flows and attractors. Recent studies suggest that the motion of galaxies within Laniakea and the Great Attractor may be influenced by structures beyond the observable universe. These so-called dark attractors, which lie outside the range of our telescopes, could represent regions of extreme density that exert gravitational influence over vast distances. If true, this would imply that the Great Attractor is just one piece of a much larger puzzle, connecting our observable universe to structures that remain hidden from view. The philosophical implications of these discoveries are profound. The Great Attractor challenges our understanding of the universe's scale and structure, forcing us to confront the limits of human knowledge. It serves as a reminder that the cosmos is far more intricate and interconnected than we can currently comprehend, and that every discovery opens the door to new questions and mysteries. As astronomers continue to study the Great Attractor, they are not only uncovering the secrets of a distant region of space, but also advancing our understanding of the universe's fundamental forces. Each observation, simulation, and discovery brings us closer to answering some of the most profound questions in cosmology, while also inspiring a sense of wonder at the vast and dynamic nature of the cosmos. The Great Attractor's mysterious nature continues to be a focal point for cutting-edge astronomical research. With its gravitational pull influencing thousands of galaxies, It has become a symbol of both the limits and the possibilities of human exploration. As we push forward with advanced technology, the study of the Great Attractor challenges us to rethink the very frameworks we use to understand the universe, from the nature of gravity to the intricate dance of matter and energy on cosmic scales. One of the key advancements driving this research is the advent of multi-wavelength astronomy. Unlike earlier studies that relied primarily on visible light, modern astronomers now have access to tools that can observe the universe across a wide range of wavelengths, from infrared to X-rays and beyond. Each wavelength provides a different perspective, revealing details that are invisible in other parts of the spectrum. For the Great Attractor, these tools have been invaluable in peering through the dense plane of the Milky Way, uncovering hidden galaxies and structures that were previously obscured. Infrared observations, for example, have been particularly effective in mapping the zone of avoidance, the region of the sky where the Great Attractor resides. Infrared light can penetrate the interstellar dust that blocks visible light, allowing astronomers to detect galaxies and clusters behind this cosmic curtain. These observations have revealed a complex tapestry of structures, hinting at the Great Attractor's true extent and composition. X-ray astronomy has added another layer of insight. By detecting the high-energy radiation emitted by hot gas and galaxy clusters, X-ray telescopes like Chandra and XMM Newton have provided a detailed view of the matter surrounding the Great Attractor. This gas, heated to millions of degrees during collisions and mergers, emits X-rays that can be used to trace the distribution of mass within clusters. These observations have helped confirm that the Great Attractor is not a single object, but a composite of multiple overlapping structures. Radio astronomy has also played a crucial role. By observing the faint radio waves emitted by neutral hydrogen gas in galaxies, astronomers have been able to map their motion and distribution with remarkable precision. These maps reveal the paths that galaxies follow as they move toward the Great Attractor, creating a three-dimensional picture of the flows of matter within this region. These flows align with the larger patterns of the cosmic web, connecting the Great Attractor to neighboring structures like the Shapley supercluster. The integration of these observations with theoretical models has led to a new understanding of the Great Attractor's role in the cosmic hierarchy. Simulations of large-scale structure formation suggest that regions like the Great Attractor are not static. They evolve over time through a combination of gravitational attraction, mergers, and interactions with neighboring structures. These simulations, run on some of the world's most powerful supercomputers, have provided a dynamic view of the Great Attractor's past, present, and potential future. One of the most intriguing findings from these simulations is the realization that the Great Attractor's influence extends far beyond its immediate region. Its gravitational pull is part of a larger network of forces that shape the motion of galaxies across millions of light years. This network includes not only the Shapley supercluster, but also other massive structures, some of which may lie beyond the observable universe. These connections suggest that the Great Attractor is just one node in a much larger system, highlighting the interconnectedness of the cosmos on its grandest scales. As technology continues to advance, astronomers are looking to the next generation of observatories to provide even deeper insights into the Great Attractor. The James Webb Space Telescope, with its unparalleled infrared capabilities, promises to reveal new details about the galaxies hidden within the zone of avoidance. Meanwhile, radio observatories like the Square Kilometre Array will map the motion of galaxies with unprecedented precision, shedding light on the flows of matter within the Great Attractor and beyond. At the same time, advances in gravitational wave astronomy offer an entirely new way to study the Great Attractor. Gravitational waves, ripples in space-time caused by massive events like galaxy mergers, could provide indirect evidence of the interactions and dynamics within this region. By detecting these waves, astronomers may be able to probe the hidden processes that have shaped the Great Attractor over billions of years. Despite these advances, many questions about the Great Attractor remain unanswered. What is its ultimate fate? Will its gravitational pull continue to dominate, drawing more matter inward? Or will the accelerating expansion of the universe eventually overpower it? How does its mass compare to other structures in the universe? And what does this tell us about the distribution of matter on the largest scales? And perhaps most intriguingly, What role does dark matter play in its formation and evolution? The answers to these questions have profound implications for our understanding of the universe. They will shed light on the fundamental forces that govern cosmic structure, from gravity and dark matter to dark energy. They will also help us place the Great Attractor within the larger context of the universe's evolution, revealing how regions like this fit into the story of the cosmos. As we continue to explore the Great Attractor, we are reminded of the vastness of the universe and the mysteries that lie within it. Each discovery brings us closer to understanding this enigmatic region, but it also opens new doors, inspiring us to look further and deeper into the cosmos. The Great Attractor is not just a gravitational anomaly. It is a symbol of humanity's quest to uncover the secrets of the universe, a journey that will continue to push the boundaries of knowledge and imagination. As the Great Attractor exerts its gravitational pull on thousands of galaxies, it becomes increasingly clear that its influence extends beyond immediate physical interactions. Its existence prompts profound questions about the underlying principles governing the universe. While its mass and gravitational effects are tangible, the implications of the Great Attractor stretch into the realms of theoretical physics, cosmology, and even philosophy. What does it tell us about the nature of the cosmos, and what deeper truths might it reveal? The Great Attractor represents an intricate interplay of forces, where gravity dominates, but does not act alone. Dark matter, the unseen yet pervasive scaffolding of the universe, is central to its gravitational power. Observations suggest that visible matter, galaxies, stars, and intergalactic gas, accounts for only a fraction of the Great Attractor's total mass. The remainder is attributed to dark matter, which interacts gravitationally but remains invisible to telescopes. Understanding how this dark matter is distributed within the Great Attractor is crucial for explaining its gravitational effects and its role in the larger cosmic web. Dark matter itself is one of the most profound mysteries in astrophysics. It constitutes about 27% of the universe's total mass energy content, yet its true nature remains elusive. Various theories propose that dark matter could consist of weakly interacting massive particles, WIMPs, axions, or other exotic particles. The study of regions like the Great Attractor provides a unique opportunity to test these theories, as the gravitational effects of dark matter are amplified in such dense, massive regions. While dark matter shapes the structure of the Great Attractor, dark energy influences its fate. This enigmatic force, which makes up approximately 68% of the universe's mass energy content, drives the accelerated expansion of the universe. On the largest scales, dark energy acts as a counterforce to gravity, pushing galaxies apart and diluting the influence of massive structures like the Great Attractor. The interplay between these two forces, gravity pulling matter together and dark energy pushing it apart, defines the dynamics of the cosmos. The balance between gravity and dark energy raises intriguing questions about the future of the Great Attractor. If dark energy continues to dominate, its effects could eventually overpower the gravitational pull of the Great Attractor, halting the flow of galaxies toward it and isolating them in an ever-expanding void. Alternatively, if dark energy weakens or behaves differently over time, gravity could reclaim dominance, leading to continued growth and clustering within the Great Attractor. This interplay also provides clues about the ultimate fate of the universe. Cosmologists have proposed several scenarios, from the Big Rip, where dark energy tears apart galaxies and atoms, to the Big Freeze, where expansion leads to a cold, dark, and sparsely populated universe. The Great Attractor, as a dense region of matter, offers a microcosm for studying these processes and understanding how they might unfold on larger scales. Another fascinating implication of the Great Attractor lies in its connection to the cosmic web. The web's intricate filaments and nodes represent the universe's large-scale structure, shaped by gravity over billions of years. The Great Attractor, as a node within this web, demonstrates how matter organizes itself into complex patterns, guided by the interplay of gravitational forces and the distribution of dark matter. By studying the Great Attractor, astronomers gain insights into the processes that govern the formation of superclusters, voids, and the overall architecture of the cosmos. The philosophical dimensions of the Great Attractor are equally profound, Its existence challenges our understanding of the universe's scale, complexity, and interconnectedness. It reminds us that the cosmos operates on levels far beyond human perception, with forces and structures that span billions of light years and billions of years. This realization forces us to confront the limits of human knowledge while inspiring a sense of wonder and curiosity about the vast unknown. The Great Attractor also invites reflection on humanity's place in the cosmos. As part of the Laniakea supercluster, our galaxy is inexorably drawn toward this massive region of space, a reminder that we are not isolated but part of a much larger system. This interconnectedness extends beyond the physical, linking the fate of our galaxy to the larger flows of matter and energy that define the universe. As we continue to study the Great Attractor, new discoveries will undoubtedly reshape our understanding of the universe. Advances in observational technology, such as next-generation telescopes and gravitational wave detectors, promise to reveal new details about its structure, composition, and motion. Theoretical advancements, including models of dark matter and dark energy, will provide deeper insights into the forces shaping its behavior. Together, these efforts will bring us closer to answering the fundamental questions posed by the Great Attractor. Despite its enigmatic nature, the Great Attractor stands as a testament to the power of human curiosity and ingenuity. It challenges us to push the boundaries of science, to look beyond what is visible and measurable, and to seek answers to questions that transcend our immediate understanding. The journey to uncover its secrets is not just a scientific endeavor, but a reminder of the vast potential of human exploration and the enduring mystery of the cosmos. The gravitational pull of the Great Attractor, though immense, is part of an even broader context that involves the dynamic interplay between various cosmic structures. While much of its mystery lies in its mass and influence, the Great Attractor also serves as a gateway to understanding the relationships among the universe's largest entities: galaxies, clusters, superclusters, and the cosmic web. These relationships are not merely static. They evolve over billions of years, creating a living, breathing cosmos shaped by forces beyond human comprehension. One of the most striking revelations about the Great Attractor is its apparent connection to the Shapley supercluster. Located further along the same gravitational flow, Shapley is one of the most massive known superclusters, with a mass far exceeding that of the Great Attractor. This raises a tantalizing question. Is the Great Attractor merely a waypoint in the cosmic flow, with galaxies ultimately destined for the Shapley supercluster? If so, this would redefine our understanding of how matter moves and organizes itself on the largest scales. The Shapley supercluster, like the Great Attractor, exerts a gravitational influence that extends across hundreds of millions of light years. Its mass and position create a complex gravitational field, pulling galaxies and clusters from all directions. The interaction between these two massive regions, the Great Attractor and Shapley, creates a cosmic tug-of-war, shaping the motion of galaxies caught in their overlapping spheres of influence. This interplay highlights the hierarchical nature of the universe, where smaller attractors feed into larger ones, forming a cascading system of gravitational flows. To better understand this dynamic, astronomers have developed sophisticated simulations that model the motion of galaxies under the influence of gravity. These simulations incorporate data from large-scale galaxy surveys, such as the Sloan Digital Sky Survey, and combine it with theoretical models of dark matter and dark energy. The resulting models reveal how matter flows through the cosmic web, moving along filaments and converging at dense nodes like the Great Attractor and Shapley supercluster. They also show how these flows evolve over time, offering a glimpse into the future of these structures. The study of these flows has uncovered patterns that challenge conventional assumptions about the universe's organization. For instance, while the Great Attractor was initially thought to be the ultimate destination for galaxies within its region, newer data suggests that it may play a transitional role, redirecting matter towards Shapley or other distant attractors. This raises profound questions about the nature of attractors themselves. Are they permanent fixtures in the cosmic landscape, or do they evolve and dissolve as matter redistributes over time? Another layer of complexity is added by the influence of dark energy. This mysterious force, which drives the universe's accelerated expansion, acts against gravity, pushing galaxies apart and diluting the influence of massive structures like the Great Attractor. Over billions of years, dark energy's dominance could alter the flow of matter within the cosmic web, isolating regions like the Great Attractor from the larger network. This interplay between gravity and dark energy underscores the dynamic nature of the universe, where forces compete and interact to shape its evolution. The motion of galaxies within the Great Attractor's region also provides valuable insights into the nature of cosmic flows. These flows are not uniform, but follow intricate paths defined by the distribution of matter and the curvature of space-time. By mapping these paths, astronomers can reconstruct the gravitational landscape of the Great Attractor and its surroundings, revealing the hidden structure of the cosmic web. This mapping has already uncovered filaments of matter connecting the Great Attractor to other nodes, including Shapley, further emphasizing its role as a nexus within the larger cosmic network. The study of these flows has also highlighted the importance of intergalactic gas in tracing the motion of galaxies. This hot, diffuse gas, heated to millions of degrees during collisions and mergers, emits X-rays that can be detected by space-based observatories. By analyzing these X-rays, astronomers can determine the temperature, density, and distribution of the gas, which in turn provides clues about the gravitational forces at work. These observations have revealed shock waves and turbulence within the Great Attractor's region, evidence of past interactions and ongoing dynamics. While much progress has been made in understanding the Great Attractor, many mysteries remain. For instance, what role do unseen forces play in shaping its gravitational field? Could there be exotic phenomena, such as massive black holes or undiscovered types of dark matter, contributing to its mass? And how does the Great Attractor's influence compare to that of other massive structures in the universe? These questions drive ongoing research, pushing the boundaries of both observation and theory. The Great Attractor also serves as a reminder of the interconnectedness of the universe. Its gravitational pull is not an isolated phenomenon, but part of a larger system of forces that binds the cosmos together. Each discovery about its nature and influence deepens our understanding of this system, revealing the intricate dance of matter and energy that defines the universe on its largest scales. As we continue to study the Great Attractor, we are not just unraveling the mysteries of a single region of space. We are exploring the fundamental principles that govern the cosmos. From the behavior of dark matter and dark energy to the dynamics of cosmic flows, the Great Attractor offers a window into the forces that shape our universe. Its study is a testament to humanity's relentless curiosity and our drive to uncover the hidden truths of the cosmos. The Great Attractor serves as a celestial cornerstone in the study of the universe's large-scale structure, yet its mystery deepens with every discovery. While it exerts a gravitational influence on thousands of galaxies within the Laniakea supercluster, its connection to the cosmic web and other attractors, such as the Shapley supercluster, suggests that it is part of an even more intricate and dynamic hierarchy. This realization has inspired astronomers to delve deeper into its origins, its role in the cosmic flow, and the fundamental forces shaping its behavior. At the heart of the Great Attractor's mystery is its apparent complexity. Initial observations suggested that it might be a single, dense concentration of matter. However, as technology advanced and our understanding of cosmic structures evolved, it became clear that the Great Attractor is not a singular entity. Instead, it appears to be a composite of overlapping galaxy clusters, intergalactic gas, and dark matter filaments, all interacting gravitationally to create the massive pull observed in its region. This complexity poses significant challenges for astronomers. Identifying the individual components of the Great Attractor requires detailed observations across multiple wavelengths, from infrared and X-rays to radio waves. Each wavelength provides a unique piece of the puzzle, revealing different aspects of the structure. For example, infrared observations can penetrate the dense dust of the zone of avoidance to uncover hidden galaxies, while X-rays trace the hot gas that fills galaxy clusters, highlighting regions of intense gravitational interaction. One of the most valuable tools in this investigation has been the study of peculiar velocities. By measuring the motion of galaxies relative to the cosmic microwave background, the remnant radiation of the Big Bang, astronomers can detect deviations from the expected flow of cosmic expansion. These deviations, caused by the gravitational pull of massive structures like the Great Attractor, provide crucial data for mapping its influence and estimating its mass. The results of these studies have consistently pointed to a gravitational force far exceeding what can be accounted for by visible matter alone, reinforcing the importance of dark matter in shaping the Great Attractor. Dark matter, though invisible, is thought to form the backbone of the Great Attractor's mass. Its presence is inferred through its gravitational effects, which dominate the motion of galaxies and clusters in the region. Advanced simulations of dark matter dynamics have helped scientists visualize how this elusive substance forms the dense filaments and nodes of the cosmic web, guiding the flow of matter toward attractors like the Great Attractor and Shapley supercluster. These simulations also highlight the role of dark matter in the early universe, where its gravitational pull seeded the formation of large-scale structures. The interplay between dark matter and visible matter is further complicated by the presence of intergalactic gas. This hot, ionized gas, which emits X-rays detectable by space-based telescopes, serves as both a marker of gravitational interactions and a driver of galaxy evolution. Within the Great Attractor, the distribution of this gas reveals regions of past and ongoing collisions between galaxy clusters. These collisions create shockwaves that heat the gas and redistribute matter, leaving observable signatures that astronomers can use to reconstruct the region's history. One of the most significant questions surrounding the Great Attractor is its ultimate fate. While its gravitational pull currently dominates the motion of galaxies within its reach, the accelerating expansion of the universe driven by dark energy poses a challenge to its influence. Over time, dark energy's effects could isolate the Great Attractor, halting the flow of galaxies toward it and dispersing its surrounding matter into the cosmic void. Alternatively, if dark energy's behavior changes, gravity could reclaim dominance, allowing the Great Attractor to continue growing and merging with other structures. This tension between attraction and expansion highlights the dynamic nature of the universe. The Great Attractor is not a static feature, but an evolving system, shaped by the forces of gravity, dark matter, and dark energy. Its role in the cosmic web reflects this dynamism, as it acts not only as a gravitational center, but also as a waypoint in the flow of matter across the universe. This dual role underscores the interconnectedness of cosmic structures and the complexity of their interactions. Recent advances in observational technology have opened new avenues for studying the Great Attractor. The James Webb Space Telescope, with its infrared capabilities, promises to uncover previously hidden details about the galaxies and clusters within the zone of avoidance. Radio observatories like the Square Kilometre Array will provide high-resolution maps of neutral hydrogen gas, offering new insights into the motion and distribution of galaxies. Meanwhile, gravitational wave detectors could reveal the signatures of massive collisions and mergers within the Great Attractor, providing a completely new perspective on its dynamics. These tools not only enhance our understanding of the Great Attractor, but also contribute to broader questions about the universe's structure and evolution. By studying the Great Attractor, scientists are exploring the fundamental forces that govern the cosmos, from the behavior of dark matter and dark energy to the interplay of galaxies, clusters, and superclusters. Each discovery brings us closer to unraveling the mysteries of the universe, while raising new questions about the nature of reality itself. The Great Attractor remains a focal point of scientific curiosity and exploration. Its study is a testament to humanity's relentless drive to understand the cosmos, to look beyond what is visible, and to uncover the hidden forces that shape our universe. As our tools and techniques continue to improve, the secrets of the Great Attractor will slowly come to light, revealing not only the nature of this enigmatic region, but also the deeper truths that define the universe. As we delve deeper into the Great Attractor's mysteries, its significance extends beyond its gravitational influence. This massive cosmic anomaly forces us to reconsider the principles that govern the universe, revealing connections between observed phenomena and theoretical frameworks. It exemplifies the complexity of cosmic evolution and the interplay of forces that have shaped the universe over billions of years. Each discovery about the Great Attractor not only enhances our understanding of this region, but also redefines our perspective on the cosmos as a whole. One of the most compelling aspects of the Great Attractor is its role in the motion of our own galaxy. The Milky Way, along with the Andromeda Galaxy and other members of the local group, is moving toward the Great Attractor at a remarkable speed of approximately 600 kilometers per second. This motion is part of a larger flow that includes neighboring clusters and groups, all converging toward the dense regions defined by the Great Attractor and, further beyond, the Shapley supercluster. Understanding this motion requires precise measurements of galaxy velocities and their deviations from the cosmic expansion. These peculiar velocities provide a unique window into the gravitational forces at play, mapping the contours of the Great Attractor's influence. Observations of the local group's motion have also revealed subtleties in the flow, suggesting that the gravitational pull of the Great Attractor is not uniform, but shaped by the distribution of matter, both visible and dark, within its region. The influence of the Great Attractor extends far beyond its immediate surroundings. By tracing the motion of galaxies over vast distances, astronomers have discovered that the Great Attractor is part of a network of gravitational interactions that shape the flow of matter across the cosmic web. This network connects nodes like the Great Attractor to other massive structures, such as the Shapley supercluster and potentially unseen attractors beyond the observable universe. These connections highlight the interdependence of cosmic structures, where each node influences and is influenced by the others. The discovery of the Laniakea supercluster has been instrumental in placing the Great Attractor within this larger context. Laniakea, which encompasses the Milky Way and thousands of other galaxies, is defined by the flow of matter toward the Great Attractor. However, its boundaries are not fixed, but determined by the gravitational interactions that govern the motion of galaxies within its domain. This dynamic nature reflects the evolving structure of the universe, where gravity and dark energy constantly reshape the distribution of matter. The role of dark matter in these interactions cannot be overstated. Dark matter, which makes up the majority of the universe's mass, forms the invisible scaffolding that underpins the cosmic web. Within the Great Attractor, dark matter's gravitational influence shapes the motion of galaxies and clusters, guiding them along filaments toward dense nodes. Advanced simulations of dark matter dynamics have provided insights into how these filaments form and evolve, revealing patterns that mirror the flows of visible matter. Dark energy, on the other hand, complicates this picture by driving the accelerated expansion of the universe. Its effects become increasingly pronounced on the largest scales, pushing galaxies apart and counteracting the pull of gravity. The balance between dark energy and gravity defines the behavior of structures like the Great Attractor, determining whether they continue to grow or eventually lose their influence. This interplay raises fundamental questions about the nature of dark energy and its role in the universe's ultimate fate. Observational advancements are helping astronomers probe these questions with greater precision. Next-generation telescopes, such as the James Webb Space Telescope and upcoming radio arrays, are poised to uncover new details about the Great Attractor and its surrounding regions. These instruments will provide higher-resolution maps of galaxy distribution, motion, and composition, offering a clearer picture of the forces shaping this region. At the same time, theoretical developments are pushing the boundaries of our understanding. Models of large-scale structure formation, informed by both observations and simulations, are providing new insights into the behavior of matter and energy within the cosmic web. These models suggest that regions like the Great Attractor are not static, but evolve through a series of interactions, from mergers and collisions to the gradual accretion of matter along filaments. Despite these advances, many mysteries remain. The exact composition of the Great Attractor, its connection to larger structures like Shapley, and its ultimate fate all pose questions that challenge current theories. Moreover, the possibility of undiscovered phenomena, such as exotic forms of dark matter or hidden attractors beyond the observable universe, adds layers of complexity to this already intricate puzzle. The philosophical implications of the Great Attractor are equally profound. It serves as a reminder of humanity's place within an immense, interconnected cosmos, where forces beyond our immediate perception shape the very fabric of reality. The study of the Great Attractor not only deepens our understanding of the universe, but also inspires a sense of wonder and curiosity about the mysteries that lie beyond. As our tools and techniques continue to improve, the Great Attractor will undoubtedly yield more of its secrets. Each discovery will not only illuminate this enigmatic region, but also contribute to a broader understanding of the universe's structure, dynamics, and evolution. The journey to uncover the Great Attractor's nature is a testament to the power of human ingenuity and the enduring quest to explore the unknown. The Great Attractor is a dynamic hub within the universe's vast network of gravitational interactions. While its immense pull on galaxies reveals a great deal about its mass and influence, its location within the cosmic web and its relationships to other massive structures offer even deeper insights into the interconnected nature of the cosmos. As astronomers continue to map its effects, the Great Attractor serves as both a scientific mystery and a window into the mechanisms driving the universe's evolution. One of the defining features of the Great Attractor is its location in a densely populated region of the universe. This area, situated in the direction of the Hydra Centaurus supercluster, is crowded with galaxy clusters, intergalactic gas, and dark matter filaments. These components interact gravitationally, creating a complex gravitational landscape where the pull of the Great Attractor is amplified by surrounding structures. The result is a region where galaxies and clusters flow along well-defined pathways, converging toward this massive node in the cosmic web. This convergence is not random. It follows the intricate patterns of the cosmic web, a structure shaped by gravity and the distribution of dark matter. The Great Attractor occupies a central position within the Laniakea supercluster, a massive conglomeration of galaxies and clusters that spans over 500 million light-years. Within Laniakea, the Great Attractor acts as a gravitational anchor, drawing matter inward and organizing the motion of galaxies on a vast scale. However, it is not the ultimate endpoint for this flow. Beyond it lies the Shapley supercluster, whose immense gravitational influence suggests that the Great Attractor is part of a larger, interconnected system. The relationship between the Great Attractor and Shapley is a subject of ongoing investigation. Observations suggest that the gravitational pull of Shapley may rival, or even surpass that of the Great Attractor, creating a complex interplay of forces that shapes the motion of galaxies within their overlapping domains. This raises questions about the hierarchical nature of cosmic attractors. Are regions like the Great Attractor permanent features, or do they evolve and dissolve as matter redistributes over cosmic timescales? Understanding this relationship requires detailed observations of galaxy motion and the distribution of matter across vast distances. The presence of dark matter complicates this picture further. Dark matter's invisible nature makes it difficult to observe directly, but its gravitational effects are evident in the motion of galaxies and the behavior of intergalactic gas. Within the Great Attractor, dark matter likely forms a dense core surrounded by filaments that connect it to neighboring structures. These filaments guide the flow of matter, channeling galaxies and clusters toward the Great Attractor and beyond. By studying these flows, astronomers can infer the distribution of dark matter and gain insights into its role in shaping the universe. The dynamics of intergalactic gas also play a crucial role in understanding the Great Attractor. This gas, heated to millions of degrees during collisions and mergers, emits X-rays that can be detected by space-based telescopes. Observations of these X-rays reveal the distribution of hot gas within and around the Great Attractor, providing clues about past interactions and the gravitational forces at work. For example, shockwaves and turbulence in the gas indicate regions where galaxy clusters have collided, reshaping the distribution of matter and amplifying the gravitational pull. The Great Attractor's evolution is closely tied to these interactions. Over billions of years, galaxy clusters within its domain have likely merged, growing its mass and extending its influence. These mergers are among the most energetic events in the universe, releasing enormous amounts of heat and creating observable signatures in the surrounding gas. By studying these signatures, astronomers can reconstruct the history of the Great Attractor and understand the processes that have shaped it over time. Despite these advances, many questions about the Great Attractor remain unanswered. For instance, what lies at its core? Is it primarily composed of dark matter, or does it contain a concentration of visible galaxies and intergalactic gas that is yet to be fully observed? How does its mass compare to other structures in the universe? And what does this tell us about the distribution of matter on the largest scales? And how do its interactions with neighboring attractors, such as Shapley, influence its evolution? These questions are not merely academic. They have profound implications for our understanding of the universe. By studying the Great Attractor, astronomers are exploring the fundamental forces that govern cosmic structure, from gravity and dark matter to dark energy. Each discovery adds a new piece to the puzzle, revealing the intricate connections between galaxies, clusters, and superclusters, and the forces that bind them together. The philosophical implications of the Great Attractor are equally profound. Its existence challenges our perception of the universe, forcing us to confront the vastness and complexity of the cosmos. It serves as a reminder of the interconnectedness of all things, where the motion of galaxies within our local group is influenced by forces originating hundreds of millions of light years away. This interconnectedness underscores the unity of the universe, where every structure is part of a larger whole. As observational technology continues to improve, the Great Attractor will undoubtedly yield more of its secrets. Future missions, such as advanced X-ray and radio telescopes, promise to provide clearer views of its structure and composition. These tools, combined with theoretical models and simulations, will help astronomers unravel the mysteries of this enigmatic region and place it within the broader context of the cosmic web. The journey to understand the Great Attractor is a testament to humanity's relentless curiosity and ingenuity. It is a quest that pushes the boundaries of knowledge, revealing not only the nature of this massive region, but also the forces that shape the universe itself. As we continue to explore its mysteries, the Great Attractor stands as a symbol of our drive to uncover the hidden truths of the cosmos, inspiring new generations to look to the stars and ask questions that expand the horizons of our understanding. The Great Attractor stands as a profound reminder of the universe's interconnectedness and the sheer scale of its cosmic architecture. While its gravitational pull governs the motion of thousands of galaxies within its region, it also serves as a nexus for questions about the nature of gravity, dark matter, and dark energy. Its study is a journey that pushes the limits of our technology, challenges our theories, and reshapes our understanding of how the universe operates on its largest scales. A crucial aspect of understanding the Great Attractor lies in its relationship with other massive structures, such as the Shapley supercluster and the broader Laniakea supercluster. These connections are not merely theoretical. They are observable through the motion of galaxies and the flows of matter within the cosmic web. By tracing these flows, astronomers can map the pathways that connect the Great Attractor to neighboring regions, revealing a complex network of gravitational interactions. One of the most intriguing findings in this regard is the realization that the Great Attractor is not an endpoint for galactic motion, but a waypoint within a larger gravitational hierarchy. Beyond the Great Attractor lies the Shapley supercluster, whose immense mass draws matter from vast distances. This suggests that the galaxies moving toward the Great Attractor are ultimately being funneled towards Shapley, raising questions about the nature and role of attractors in the cosmic web. Are these regions of convergence permanent, or do they evolve as matter continues to flow and redistribute over time? The dynamics of these flows are governed by the interplay of gravity, dark matter, and dark energy. Gravity, the force that pulls matter together, is the primary driver of the flows toward the Great Attractor. Dark matter, which forms the scaffolding of the cosmic web, enhances this pull by providing the bulk of the mass that shapes the paths of galaxies. However, dark energy, with its repulsive effects on the largest scales, works against these flows, pushing galaxies apart and influencing the overall behavior of the universe. This tension between attraction and expansion defines the current era of cosmic evolution. While gravity dominates within regions like the Great Attractor, dark energy exerts an increasing influence as distances grow. The balance of these forces will determine the fate of structures like the Great Attractor. If dark energy continues to dominate, it could eventually isolate these dense regions, halting the flow of galaxies and leaving them stranded in an expanding void. Alternatively, if dark energy's behavior changes or weakens, gravity could regain control, allowing attractors like the Great Attractor to grow and merge with neighboring structures. The study of the Great Attractor also sheds light on the nature of the universe's large-scale structure. Observations reveal that the Great Attractor is not a single, compact object, but a complex assembly of galaxy clusters, intergalactic gas, and dark matter. These components interact in ways that shape the distribution of matter within its region. For example, collisions and mergers between galaxy clusters generate shockwaves and heat the surrounding gas, creating observable signatures in the X-ray spectrum. These events provide insights into the dynamics of the Great Attractor and the processes that have shaped it over billions of years. Dark matter, in particular, plays a crucial role in the Great Attractor's gravitational influence. While it cannot be observed directly, its effects are evident in the motion of galaxies and the behavior of intergalactic gas. Advanced simulations of dark matter dynamics have shown how it forms dense filaments and nodes, guiding the flow of matter through the cosmic web. Within the Great Attractor, these filaments converge, creating a gravitational center that draws galaxies inward. The presence of dark matter also raises questions about its fundamental nature. Current theories suggest that dark matter consists of weakly interacting particles, but its exact composition remains unknown. The study of the Great Attractor provides an opportunity to test these theories, as the gravitational effects of dark matter are amplified in such dense regions. By comparing observations with simulations, astronomers hope to gain new insights into this mysterious substance and its role in shaping the universe. While dark matter defines the structure of the Great Attractor, dark energy shapes its long-term evolution. Observations of the universe's expansion reveal that dark energy accelerates the separation of galaxies, counteracting the pull of gravity. This acceleration poses a challenge to structures like the Great Attractor, which rely on gravity to draw matter inward. Understanding how dark energy influences the flows of matter within the Great Attractor's region is key to unraveling its ultimate fate. Future observations and theoretical advancements promise to illuminate these mysteries further. Next-generation telescopes, such as the Vera C. Rubin Observatory and the Square Kilometre Array, will provide unprecedented detail in mapping galaxy distribution and motion. These instruments will allow astronomers to trace the flows of matter with greater precision, revealing the true extent of the Great Attractor's influence. Additionally, gravitational wave detectors could offer new insights into the dynamics of this region by detecting the signatures of massive collisions and mergers. The philosophical implications of the Great Attractor are equally profound. It challenges us to think beyond our immediate surroundings and consider the universe as a vast, interconnected system. The motion of our galaxy, the Milky Way, toward the Great Attractor is a reminder that we are part of this larger cosmic flow, influenced by forces that operate on scales far beyond human perception. This interconnectedness underscores the unity of the cosmos, where each structure contributes to the greater whole. As we continue to study the Great Attractor, we are not only uncovering the secrets of this enigmatic region, but also gaining a deeper understanding of the universe itself. Each discovery brings us closer to answering fundamental questions about the nature of gravity, dark matter, and dark energy. At the same time, it inspires a sense of wonder and curiosity, reminding us of the vast unknown that lies beyond our current knowledge. The journey to understand the Great Attractor is far from over, but every step brings new revelations and deeper insights. It is a testament to humanity's relentless pursuit of knowledge and our drive to explore the mysteries of the cosmos, pushing the boundaries of science and expanding the horizons of our understanding. The Great Attractor's mysteries continue to serve as a focal point for the most profound questions in astronomy and cosmology. Its gravitational pull on our galaxy and thousands of others has revealed insights into the mechanics of large-scale structures and the forces that govern their evolution. Yet, its nature remains elusive, hidden behind layers of complexity that challenge both observation and theory. Central to this mystery is the Great Attractor's apparent influence on the Laniakea supercluster, a structure so vast that it redefined humanity's understanding of our place in the universe. Within Laniakea, the Great Attractor acts as a gravitational anchor, organizing the motion of galaxies over hundreds of millions of light years. However, this influence does not exist in isolation. The flows of matter within Laniakea are shaped by competing forces, including the Shapley supercluster and the overarching effects of dark energy. These competing influences create a dynamic environment where the motion of galaxies is not straightforward, but follows intricate pathways defined by the distribution of mass. By tracing these pathways, astronomers have identified connections between the Great Attractor and neighboring structures, suggesting that it is part of a larger system of attractors. This interconnectedness highlights the hierarchical nature of the universe, where smaller structures feed into larger ones, forming a cascade of gravitational interactions that shapes the cosmos on the largest scales. Understanding this hierarchy requires a detailed study of the forces at play. Gravity, the primary driver of these interactions, works in concert with dark matter to guide the motion of galaxies. Within the Great Attractor, the distribution of dark matter forms the underlying framework of its gravitational pull. Observations suggest that dark matter is concentrated along filaments that extend outward, connecting the Great Attractor to other nodes in the cosmic web. These filaments serve as highways for galaxies and clusters, channeling matter toward regions of higher density. Dark energy, meanwhile, acts as a counterforce, driving the accelerated expansion of the universe and pushing galaxies apart. On the largest scales, dark energy dominates, but within dense regions like the Great Attractor, gravity still holds sway. This balance between attraction and expansion defines the behavior of the universe today and raises questions about its ultimate fate. Will dark energy eventually overpower the gravitational pull of structures like the Great Attractor, isolating them from the larger cosmic web? Or will gravity find ways to counteract this expansion, allowing these structures to grow and merge over time? The study of these questions has been revolutionized by advancements in observational technology. Infrared telescopes have been instrumental in revealing the galaxies hidden within the zone of avoidance, where the Great Attractor lies. These observations have provided a clearer picture of the distribution of visible matter in the region, highlighting the complexity of its structure. At the same time, X-ray telescopes have detected the hot gas that fills galaxy clusters, offering insights into the interactions and collisions that have shaped the Great Attractor over billions of years. Radio astronomy has also played a crucial role in mapping the motion of galaxies. By observing the faint signals emitted by neutral hydrogen gas, astronomers can measure the velocity of galaxies and trace their paths through the cosmic web. These measurements have confirmed the flows of matter toward the Great Attractor and revealed the intricate patterns of motion that define its region. Simulations of large-scale structure formation have complemented these observations, providing a theoretical framework for understanding the Great Attractor's role in the cosmic web. These simulations incorporate data on galaxy distribution, dark matter, and dark energy, creating dynamic models that replicate the motion of matter within the universe. They show how regions like the Great Attractor evolve over time, growing through the accretion of matter and merging with neighboring structures. Despite these advances, the Great Attractor remains shrouded in uncertainty. Its location behind the Milky Way's dense plain of stars, dust, and gas makes direct observation challenging, while its complex composition defies simple explanations. What lies at the core of the Great Attractor? Is it dominated by dark matter, or does visible matter play a more significant role than previously thought? Could there be exotic phenomena, such as massive black holes or undiscovered forms of matter, contributing to its mass? These questions drive ongoing research, pushing the boundaries of both observation and theory. New instruments, such as the James Webb Space Telescope and the upcoming Square Kilometer Array, promise to provide unprecedented detail in studying the Great Attractor and its surroundings. These tools will allow astronomers to probe deeper into the zone of avoidance, uncovering hidden structures and refining our understanding of this enigmatic region. The philosophical implications of the Great Attractor are profound. Its existence challenges our understanding of the universe's scale and complexity, forcing us to confront the interconnectedness of all things. The motion of our galaxy toward the Great Attractor is a reminder that we are part of a larger system, influenced by forces that operate on scales far beyond human perception. This interconnectedness highlights the unity of the cosmos, where every structure, from galaxies to superclusters, contributes to the larger whole. As we continue to study the Great Attractor, Each discovery brings new insights and raises new questions. Its gravitational pull, its place within the cosmic web, and its relationship to other structures all offer clues to the nature of the universe and the forces that shape it. The journey to understand the Great Attractor is far from over, but it is a journey that illuminates not only the mysteries of this massive region, but also the deeper truths that define our place in the cosmos. The Great Attractor, as enigmatic as it is influential, continues to captivate the imagination of astronomers and cosmologists. Its gravitational pull, its connections within the cosmic web, and its elusive nature make it a centerpiece for exploring the universe's largest-scale structures and the forces that govern them. Each layer of discovery about this gravitational anomaly not only illuminates its complexities, but also deepens our understanding of the universe as an interconnected whole. At the core of this inquiry lies the question of the Great Attractor's composition. Observational evidence strongly suggests that the visible matter, galaxies, stars, and intergalactic gas, accounts for only a fraction of its total mass. The remainder, inferred from its gravitational effects, must be dark matter. This dark matter forms the invisible backbone of the Great Attractor, shaping the flows of galaxies and clusters that converge upon it. Yet its precise distribution and properties remain shrouded in mystery. Dark matter's role in the Great Attractor exemplifies its importance in the universe's structure. Unlike visible matter, dark matter does not emit, absorb, or reflect light, making it undetectable by conventional means. Instead, its presence is revealed through its gravitational influence. Within the Great Attractor, dark matter is thought to form dense filaments that guide the motion of galaxies, connecting this region to neighboring structures in the cosmic web. These filaments act as gravitational highways, funneling matter toward regions of higher density and anchoring the Great Attractor within the larger cosmic network. Observing these filaments and their connections is a formidable challenge. The zone of avoidance, the region of the sky where the Great Attractor resides, is heavily obscured by the Milky Way's dense plain of stars and gas. This obstruction has forced astronomers to rely on alternative methods, such as infrared and X-ray observations, to peer through the galactic veil. These techniques have revealed previously hidden structures, including galaxy clusters and intergalactic gas, providing critical clues about the Great Attractor's nature. X-ray astronomy, in particular, has been instrumental in studying the hot gas that permeates galaxy clusters within the Great Attractor. This gas, heated to millions of degrees by gravitational interactions and collisions, emits high-energy radiation detectable by space-based telescopes. By analyzing these emissions, astronomers can map the distribution of mass within the Great Attractor and identify regions of past and ongoing interactions. These observations have revealed a dynamic environment where collisions and mergers between galaxy clusters reshape the region's structure over time. Infrared observations have complemented these findings by uncovering the galaxies hidden within the zone of avoidance. Infrared light can penetrate the dust that blocks visible light, revealing the distribution of stars and galaxies within this obscured region. These observations have helped astronomers map the flows of matter toward the Great Attractor, highlighting the pathways that connect it to other nodes in the cosmic web. Radio astronomy has also played a critical role in tracing the motion of galaxies within the Great Attractor's domain. By observing the faint radio signals emitted by neutral hydrogen gas, astronomers can measure galaxy velocities with remarkable precision. These measurements have confirmed that the galaxies within this region are not moving randomly, but are drawn along well-defined paths, shaped by the gravitational pull of the Great Attractor and neighboring structures. The flows of matter toward the Great Attractor are part of a larger system of cosmic flows that define the motion of galaxies across the universe. These flows are not uniform. They follow the contours of the cosmic web, guided by the distribution of dark matter and the gravitational pull of massive structures like the Great Attractor and Shapley supercluster. By studying these flows, astronomers can map the gravitational landscape of the universe, revealing how matter is organized and distributed on the largest scales. Simulations of large-scale structure formation have been invaluable in understanding these dynamics. These simulations, which incorporate data on galaxy distribution, dark matter, and dark energy, create virtual models of the universe that replicate the motion of matter within the cosmic web. They show how regions like the Great Attractor evolve over time, growing through the accretion of matter and interacting with neighboring structures. These models provide a theoretical framework for interpreting observational data and predicting the future behavior of the Great Attractor. One of the most intriguing aspects of these studies is the realization that the Great Attractor is part of a hierarchical network of attractors. Beyond the Great Attractor lies the Shapley supercluster, whose immense gravitational pull suggests that it may be the ultimate destination for the galaxies flowing through the Great Attractor's region. This raises fundamental questions about the nature of attractors themselves. Are they permanent features, or do they evolve and dissolve as matter redistributes over cosmic timescales? The presence of dark energy adds another layer of complexity to these questions. Dark energy, the mysterious force driving the universe's accelerated expansion, acts against gravity, pushing galaxies apart and influencing the flows of matter within the cosmic web. On the largest scales, dark energy dominates, but within regions like the Great Attractor, gravity still holds sway. This balance between attraction and expansion defines the behavior of the universe today and shapes the fate of structures like the Great Attractor. Despite these challenges, the study of the Great Attractor continues to yield new insights. Advances in observational technology, from next-generation telescopes to gravitational wave detectors, promise to reveal more about this enigmatic region. These tools will allow astronomers to probe deeper into the zone of avoidance, uncovering hidden structures and refining our understanding of the forces at play. The Great Attractor is more than just a gravitational anomaly. It is a symbol of the interconnectedness of the universe. Its study highlights the unity of cosmic structures, where every galaxy, cluster, and supercluster is part of a larger whole. As we continue to explore its mysteries, the Great Attractor serves as a reminder of the vast unknown that lies beyond our current understanding and the endless potential for discovery in the cosmos. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.